Before I will introduce our panelists, I'd like to share a few thoughts with you in order to set the stage for our discussion. First, I'd like to briefly explain why we chose this topic. We were inspired by a sense of urgency amongst peers and a notion that environments we build are not up to the task of creating a sustainable habitat for generations to come. To justify our decision, with a credible source, I have this excerpt from Fabricate 2020 that declares digital design and construction technologies to be central in our response to the climate and ecological emergency. In this 5-minute foreword, I'd like to focus on 4 concepts and share important perspectives that I hope will string our discussion together. I am not interested in theoretical deliberations or disputes about the nature of the generative, the parametric, the algorithmic design, etc. I am interested in the practical potential of certain perspectives. Let's start with computerization. New Leach uses that word to describe the period when old analog techniques were transferred into a digital domain, the beginning of use of computers in architectural offices. And then he adds that computerization is the act of storing information in the computer or a computer system. Computation, on the other hand, is more than that. It is the procedure of calculating, determining something by mathematical or logical methods. For architects, engineers, builders, computation begins when they begin to use computers to understand material and structural behavior. This distinction is important because it leads to a shift in thinking. Form is not a result of arbitrary decisions anymore, but is being derived from material, structural, and environmental information. One of the most rigorous and succinct distinctions between computation and computerization I found in this book edited by Aki Menges and Sean Alquist, Computational Design Thinking. Using their words, computation represents methods that deduce results from values or sets of values, while computerization describes methods that simply compile or associate given values or sets of values. If we're not using our tools to deduce our designs from the data that we have at our disposal, we're not using the tools that we have to their fullest capacity. Computational design begins when we construct systems of formally described relationships. One of the famous examples of such systems is Gaudi's analog parametric design computer. He explored some of his designs using scale models made of chains or weighted strings. They took him years to build, but gave him more flexibility to explore organic designs, since every adjustment would immediately trigger the physical recomputation of optimal arches. To summarize, computational design thinking helps designers make sense of loopy, complex systems, chunk big problems into smaller, more solvable parts, devise design systems that integrate environmental performance, manufacturing constraints, assembly logics, and material characteristics, and deduce form from those relationships. Manufacturing, assembly, and disassembly can be engaged with the environment, materials, structural, and architectural systems by means of computational design. Fundamental concepts which underlie computational theory and techniques expose form as a subsidiary component of environment. The upcoming presentations and the following discussion will help us understand how to harness information from environment, materials, and construction systems in order to construct with them our design system that have the capability to deduce shape, behavior, and the environmental impact of the artifact that we design.